So today we'll continue our discussion on modes in a planar slab waveguide. So last couple of classes we saw how to solve for the TE and TM modes, right? So today we'll look at some of the further properties of such modes. So one thing to sort of note here. So as we discussed, so these modes have a longitudinal component, right? So they are not purely TEM modes. So TE means there is a magnetic field component in the longitudinal direction, and for the TM mode there is an electric field in the longitudinal direction, right? So what is the strength of this longitudinal component compared to the transverse component? Okay, so that will tell us how close or far it is from like a purely TEM kind of wave. So if you consider the TE mode, right? So basically what we want to know is the ratio of the amplitude of the magnetic field in the longitudinal direction, Z direction, compared to the magnitude in the transverse or X direction. So recall from the Maxwell's equations, we can express both Hz and Hx in terms of Ey, right? For the TE mode. So specifically, you could write it like this. Right? So Hz, you can write it like that. Again, for recall the electric field is in the y direction like this. Right, and so we know the form of Ey, right? So for example, if we consider the symmetric modes or the even modes, right, then Ey goes or has the form cosine kappa x, right? So if we take the derivative with respect to x, so that goes as kappa times the minus, right? So if you look at the what is the maximum magnitude of Ey, that's like A, right? And what is the maximum magnitude of the derivative of Ey with respect to x? That's the amplitude here, which is kappa, right? So this ratio here is basically just kappa, right? And then we get a beta from here, right? The others cancel out. So this ratio is basically kappa over beta, right? And so if we substitute kappa in terms of beta, right? We also know the expression for that. Right? So I can also write it like that. And so recall that, right? So this beta over k naught is basically the effective index for the mode, right? So this is also like that. And recall this effective index has to lie between N2 and N1. Right, so the limiting values for this expression, so right, so this expression lies between, so if I put N1, this is 0, right? and so it's greater than 0 and less than n1 square by n2 square minus 1. Right, so that's the range. So basically this ratio is less than this n1 square minus n2 square. Right, so basically the strength of the longitudinal component compared to the transverse component depends on the index contrast, right? So recall this, we could also, so we define this as 2 delta, right? So difference in the square is normalized to the square is approximately 2 delta. Or just take n1 minus n2 by n2, that is delta. So right, so for this normalized index contrast much less than 1, you can see that this ratio is small, right? So the smaller the index difference, the smaller the longitudinal component, and the closer the wave is to a purely TEM kind of wave. Right, so this limit when the index contrast is less than 1, this is known as the weakly guiding limit. Okay, basically the wave is almost TEM, right? Because the longitudinal component is very small. Right, so this is the limit, for example, where optical fibers are operating, so-called weakly guiding. Okay, so that simplifies sort of the analysis of the modes quite a bit. So we'll see that specifically when we solve for modes in the optical fiber in the cylindrical geometry. Right, so basically, yeah, so that's one point. If delta becomes really large, right, if the index contrast becomes big, which you can have, for example, nowadays people make on-chip photonic devices, and there, like the guidance is very strong. So people make very sub-wavelength structures, and the index contrast is large. For example, you could have silicon in the core and silicon dioxide in the cladding, and so the index difference is actually of the order of the index itself. Okay, so silicon, for example, has index 3.4, and the cladding silica glass has 1.5. Right? So the difference is 2, which is of the order of the index itself. Right? So then you're not in this limit at all. And in that case, the longitudinal components are very strong, right? And yeah, you can no longer approximate them as TEM waves. So, and they're like even. So basically, you have to consider longitudinal component. You can't neglect that for most purposes. But whereas in the weakly guiding limit, for a lot of things, you can neglect the longitudinal component. Okay, so that's one thing to discuss. The other is that, so how do we decide which modes are guided, right? So we have, for example, some TE modes and some TM modes supported in the structure. So which ones are guided, of course, depends on how we excite the waveguide, right? So N1, N2, and this is D. So which modes actually propagate here depends on how, so for example, we are coupling from free space and some focusing light into the waveguide. Field pattern at the input, right? And also the polarization, right? So recall so for TE modes, the electric field is parallel to the y direction coming out of the board, right? And for TM modes, in this, if we consider this weakly guiding approximation, right? Although there is an EZ that is much smaller than EX, like again, so you can do the same thing for TM mode and find out EZ by EX, and it's the same thing. So basically, it is almost parallel to X for the TM mode. Okay? And even if you don't neglect the longitudinal component, at least there is a component of E along X, right, which is not there in TE. So now, depending on the input polarization, let's say, so if my input polarization is, right, so that depends on the light, so light coming from free space that I'm coupling in. So let's say that's coming from some laser source or something. So the polarization of that, if it's, let's say for example, Y, right, then I'll only excite TE modes, right. So basically, which modes are excited depends on the overlap of, or so-called overlap integral of my input field profile with the guided mode profile, right. So something like, right, so you have some E input here. So, and if you look at some guided mode and the electric field profile for that, so let's say I'm looking at some TEM mode, then basically the overlap, and then I integrate over space, right? So what this quantity is decides sort of what is the strength of the mode of the mth mode which is excited, right? So for example, if this is Y, then you can see the overlap with, so this dot product with the TE mode, which is also in Y direction, will be significant, but the overlap with the TM mode will be 0 because for the TM mode it's polarized orthogonally, right? So you will only excite TE modes if the polarization is Y. Similarly, if the polarization is X, you will only excite TM modes, right? And which TE or TM, which mth mode is excited depends on this overlap integral. Okay. So for example, if my profile at the input is an even profile, right? So symmetric about X equal to 0, then I'll only excite the even modes because the overlap integral with the odd mode will be 0. Okay, so that's how I can control to some extent which modes are excited and guided by controlling my input field profile and polarization carefully. Right, so what happens, for example, if I excite some linear polarization which is not X or Y but somewhere in the middle, right? So let's say diagonally polarized in the XY plane. Okay, so let's say my input polarization is something like that, right? So now it has components in both X and Y, so it will excite both TE and TM modes. Okay, and now both TE and TM modes will propagate. Right, so what happens? Okay, so going back, so if you excite only TE modes or only TM modes, then the polarization remains the same, right? For example, if you excite TE mode, then the polarization remains Y along the waveguide as the mode is propagating. Similarly for TE. But now, if I am exciting both TE and TM modes, then basically the polarization is not conserved, right? Why? Because so this will excite TE modes, this will excite TM modes, right? And as you know, both of them have different propagation constants. So this will acquire a phase which is, let's say, TE, beta TEZ, right? And this one will acquire, oh sorry, the other way around. So this will be TM, and this will be TE, right? And these are not equal, right? So for the same mode index also, these are not equal, right, at some particular wavelength. So what happens is, as the wave propagates, so now there will be a phase difference, right? After some distance of propagation, you can see that there will be a phase difference between the X and Y components, right? And that phase difference, so like after some propagation, I can write this sort of something like, some phase difference phi between the x and y components, right? After some distance of propagation, so y dependent z. So this phi of z, like you can see from here, is basically the difference in the propagation constants times the distance, right? So delta beta times z. And as this phase difference changes, you know the polarization vector changes, right? So for example, if this phase difference becomes pi by 2, that's like a circular polarization, right? For any other intermediate phase difference, it's like an elliptical polarization. And once this becomes, for example, pi, then it becomes x minus y. So basically, if you look along the waveguide, so you launch. So this is now in the xy plane. Okay, so maybe I should. Right, so now I'm drawing the polarization in the xy plane. So let's say you start with something which is 45, right? Then after some distance, like it becomes sort of elliptically polarized. Then after some time, it becomes circular, or after some distance. Then it becomes elliptical again. Then it becomes linear, sort of in the minus 45, right? And as you keep going, like you sort of retrace this in the opposite direction. And then you, after some distance of propagation, when this phase difference becomes 2 pi, you come back to your original polarization. Right, so basically, if you're exciting both T and TM modes, then your polarization is not constant along the waveguide and it keeps evolving, right? And this length, after which it comes back to the original polarization, that's known as the beat length. Right, so that's when this phase difference becomes 2 pi, right? So delta beta times that distance, which is the beat length, is equal to 2 pi. So basically the beat length you can see is 2 pi over delta beta. Right, so if this index contrast is small, again in the weakly guiding limit, basically what happens is T and TM modes have very close propagation constants, right? So in the limit, when you go to a TEM wave, then TE and TM are actually the same, right? Because in both cases, E and H, like if you have a purely TEM wave, then basically you have E and H both perpendicular to the propagation direction, right? So in the limit, for example, delta goes to 0, TE and TM are both the same wave, which is the TEM wave, right? And for small values of delta, the difference in this propagation constant is very small. As you increase this index contrast, the difference in the propagation constant goes up, right? So, and you can see the beat length is inversely proportional to the to this difference in the propagation constant. So in the weakly guiding limit, the beat lengths are usually longer, but if the index contrast goes up, then the beat length is smaller. Basically, the polarization changes faster. So there is a question why this delta beta would change. I mean, delta beta is not changing, right? The polarization is changing because delta beta times z is changing. As you propagate in z, the phase acquired by TE and TM, so the x and y polarization is different, right? So there is a phase difference. So delta beta is constant, right? It just depends on. So once we have a structure, we solve for the mode, we know what beta for TE and beta for TM is, and delta beta is a constant. So this is happening because as you propagate delta beta times z, as you propagate in z, this phase is changing.
Sir, excuse me, sir. Excuse me, sir.
So,
excuse me, sir.
Put some typical numbers. like for example, so if you take for example a large index contrast waveguide, like so N1 is 1.5, N2 is 1. Okay, so this is a very thin slab, 0.5 micron, but the index contrast is large, right? So if you look at a wavelength of 1.3 micron, you get that V number to be about 3. Okay, so 3 means it's less than pi, which means only the first fundamental mode is supported for both TE and TM, right? So there's TE0 mode. So basically for the TE0 mode, the beta propagation constant is about 1.34 times K0, and for the TM0 is 1.25, right? So for the TM mode, it is slightly smaller than the TE mode. Okay, so then if you calculate this 2 pi over delta beta, so that beat length comes out to be about only 15 micron. Okay, so you can see for this large index contrast, the beat length is very small. Okay? 15 microns. Within 15 microns, the polarization undergoes this change and comes back. So now if you go to weakly guiding limits, like for example, if you make this like 1.49 or something, where this index is very small, so now the beat length will go up to, for example, many meters or kilometers. Okay. Okay, so I hope that's clear. So the next thing we are interested in, of course, so any electromagnetic wave carries some power, right? Like for waveguides or fibers, also we are interested in transporting like optical signals, so they carry some power, right? So next thing we look at is what is the power carried by these T and TM modes in terms of the amplitude and the
Excuse me, sir.
amplitude of the wave and the dimensions of the structure.
Hello.
Yes?
Sir, screen is black.
Okay, so there's another question. How does N1 minus N2 small? Yeah, so by weakly guiding, what we mean is, so for example, you know that in free space, a plane wave is transverse electromagnetic, right? It's TEM. So basically, if you solve in free space or in a homogeneous medium, right, where the refractive index is constant everywhere, you get what are known as TEM waves, right? So electric and magnetic field are both perpendicular to the propagation direction. Now, if you have any structure which guides waves like this, like what we saw in the planar waveguide, right? You take any kind of waveguide where basically now you have structuring, which means like in some region there is some different refractive index, in another region there is another different refractive index, right? So overall, if you look at the medium as a whole, now it's an inhomogeneous medium, it's not a homogeneous medium anymore, right? So in that case, as we saw, when you solve for the modes, purely TEM modes are not possible anymore. Okay, so as soon as you have this refractive index variation, and you want to solve for guided modes, you see that you cannot have purely TEM modes anymore, right? But in this weakly guiding approximation, when N1 is almost close to N2, right, which means that the medium almost looks homogeneous, right? There is a very small change. So the waves, as we saw, the longitudinal component is very small, and the wave is almost TEM, right? So it almost looks like the wave is sort of like a
free space or be traveling in a homogeneous medium. That's why it's called weakly guiding, because the guidance. So you can imagine that this wave guiding is introducing a longitudinal component, right? And the stronger the wave guiding, the larger the longitudinal component, right? So in the weakly guiding approximation, why is it called weakly guiding? Is because that the longitudinal component is small and it almost looks as if the wave is just traveling in some homogeneous medium. Okay. Right. So now let's see what is the power carried by a mode of this waveguide. Right. So again, recall we calculate the power by using the pointing vector or the time average pointing vector, which you can calculate like this. Right. So we know the expressions for the electric and magnetic fields for the TE and TM mode, right, which we solved for. So using those expressions, we can find out the pointing vector and then integrate over the cross-sectional area to find out the power carry. Right? So for the TE mode, you know E is like this, right? And H, I can write like so Hx component and then Hz component, right? So this Hx again I can write in terms of the electric field. Right. And then this Z is right. So we have complete expression for the electric and magnetic field, right? So this EY, for example, for the symmetric mode, it's like cosine, and then we can calculate what Hx and Hz is also. So as again, so this waveguide is basically, so you have some mode which is traveling in the Z direction, right? So basically, we are interested in the power flow in the Z direction, the propagation direction, right? So basically, we want the component of S in the Z direction, right? So that will, you can see, come from, so we have E in the Y direction. So we take, if we take the X component of H, then that will give me S in the Z direction. Right, and if I plug in this for Hx, basically you see I get this. Right? So one thing you can check is if I look at the power flow in the X direction, right, which means it will be Ey then Hz, you can see the average of that is actually 0. Right? Why? Because so there is an I here, right? So there is an iota here, which will come here, and then you take the real part, so that's 0. So there is no power flow along the X direction, which makes sense, right? It's a guided mode traveling in the Z direction. But yeah, it also mathematically is consistent. Right, so now the power carried, so S, you know, is basically intensity, right? So this is watt per meter square. So to calculate the power, we need to integrate over the cross-sectional area. So the XY plane, right? But for this structure, it's infinite in the Y direction, right? So basically what we can do is calculate the power flow per unit length in the Y direction, because it just extends infinitely in the Y direction, right? So this will be power per unit length
in y direction, right? So these are units of watt per meter. So that will be if I integrate this Sz, which is a function of x, right, over x over this transverse coordinate. Okay, so yeah, basically we just plug in this expression. Okay, and now we just use the expression for the mode profile here, right? So for TE mode, we know there's sine and cosine in the core and then exponentially deepening the cladding, right? So again, we can take symmetric and anti-symmetric mode separately. So if I take a symmetric mode or the even mode, then this is basically A cosine kappa S, right? So A is basically the amplitude of the wave at x equals 0, right? So that's A. Or basically the electric field amplitude at x equals 0, right? That's A. Right, so basically this integral I can divide, so again the structure is symmetric about x equal to 0, right? So I can just do twice the integral from 0 to infinity. So, and then the 0 to infinity I have first from 0 to d by 2, the core region, and then the cladding region, right? So the first integral here will go from 0 to d by 2, and that will be this cosine square, and then b by 2 to infinity, right? And there, so in the core, if remember we have solution like this, and then in the cladding I have solution like this. Right, and we can relate A and C again from the boundary condition here, right? So basically A cosine kappa d by 2 is C e to the minus gamma d by 2. Right? So I can put C is equal to A cosine kappa d by 2 times e to the gamma d by 2. Right? Here. So then okay, and then so this cosine square, again you know how to integrate that, so you write this as cosine square theta is 1 plus cos 2 theta by 2, right? So and then these are now straightforward integrals. So first is a constant term, so you get d by 2, and right, so for the second you get this sine term. Right, and then here I substitute c in terms of a, right, and then I have the exponential integral. So I get that. Okay. So this 1 over gamma is coming from the integral here, right? and then this cosine cup square is coming from the relation of C to A. Okay, so we can simplify this expression more, get a simpler form. Okay, so what we do is, so write the sign here as like that, right? And I can write this as 1 minus sine square. Okay, so okay, so from this 1 here you get a 1 over gamma. We also take this 2 out here, so we get 4 here. So then we have right, d from here, and then 2 over gamma from here. We had 1 over gamma, and then we take the 2 out common, so we get 2 over gamma. All right, and then for the remaining sinusoidal terms, you basically get this. Right, so we had a sine cos here, so that's the first term, and the second term is sine square, so that's sine cos multiplied by tan. Right. So this term in the bracket here, that should be familiar, right? That's basically the transcendental equation, right? So this is 0. So remember the transcendental equation was like that, right? And this, so this was kappa d by 2. Right, so if I cancel out the d by 2, this is basically the transcendental. Right, so this term goes away. So the expression simplifies to very simple form. Okay, so the power carried per unit length in the y direction for the symmetric TE mode, right, is given by that expression. So of course it depends on the square of the electric field amplitude. So the higher the amplitude, the more power you carry, right? So again, that depends on how much power I'm launching at the input. And then it depends on the propagation constant and the dimension, the thickness of the core, right? And then gamma, which also basically depends on the propagation constant. Okay, so yeah. So typically gamma is basically right, how much the field is leaking into the cladding, right? So typically gamma is larger for the lower order modes. So this decays faster, right? For the higher order modes, this decays more slowly. So more of the field goes into the cladding. But yeah, so this is for the TE mode. So you can try at home that now take the antisymmetric mode, right? So then you start with sine. So here you'll have sine, but you sort of follow the same procedure, you get the same expression. Okay. So this is true for both for any m. both even and odd. And then we can do a similar exercise for the TM mode, right? So for the TM mode, I'll start with H in the y direction, write E like this, and again, this will be proportional to Hy and d, Hy by dx, plus I'll also have a 1 over n square from the epsilon. Right? Instead of mu, I'll have epsilon, so that will have a 1 over n square. So anyway, so you do the same procedure. For a TM mode, the expressions are a bit more complicated. Again, basically being complicated by that n1 square, that n square coming in, right? So here you'll have 1 by n1 square, and here you'll have 1 by n2 square. So if you do the exercise for TM modes, so what you get is something like that. So now the second term is more complicated. Okay, you get something like that. So again, you get, so the first term is like proportional to the thickness, and then second term is much more complicated now, okay, because you have n1 and n2.
Sir, do we have to derive it in the exams? TM mode.
Sorry?
Do we have to derive this TM mode during our exams? Or can we just remember the formula?
I mean, you don't have to remember these complicated formulas. For the exams, you'll have access to your notes and books, so there's no need to remember the complicated formulas. Just try to sort of have an idea of how things scale with each other, right? So it's proportional to the thickness and things like that. You don't need to remember the complete expressions here. But whatever I'm telling you to try at home, do try to derive them at home, right?
No, sir, I'm just asking that the transverse mode, you just wrote the formula, right? But you derived the transverse electric mode. In the book also it is given like this only. For transverse magnetic mode, this one is given only the formula. So do we have to derive it ourselves?
Yeah, I mean, for your own satisfaction, you should try and derive it and see if it's correct. Right?
Okay.
For the exam, I don't know. I mean, I'll see if if it's a limited time exam, so I'll have to give you questions which can be solved with a reasonable amount of time, right? If it's very complicated and takes too long a time, then probably not. But whatever I am skipping and trying to tell you to sort of derive at home, you should at least try to do that.
Okay, sir.
So can you
But
provide some questions for
for
practice?
the antisymmetric modes, you can easily check. That should not be too complicated. But for the TM mode, yeah, the integral does become a little bit complicated. But
Excuse me, sir.
yeah,
So can you provide some questions for practice? Some tutorial sheet?
question. So, on all the textbooks, at the end of each chapter, there are questions, so you can try solving them. If you want even more, then I mean, these are like standard topics, so you can search online, like some NPTEL course or a lot of resources. But I think even if you just do the questions at the end of the chapters in the books, that already should be enough. Okay, so right, so that's about the power carried. So another way to see here is like for a given power which is launched, right? If the waveguide is thinner, then I have a higher electric field in the waveguide, right? So the light is more intense. If the waveguide is smaller for the same amount of launch power, right, which also makes sense. Okay. So now let's look at some general properties of guided modes, right, which sort of are true for modes in any kind of waveguide, right, not just these planar waveguides, but some general properties of modes which are useful. Right, so in general, like you could have a waveguide which has some particular cross section, right? So let's say that's the XY direction, and then it's invariant in the Z direction, the propagation direction. Right, so for example, for an optical fiber, this cross section is like circular, right? And then the structure extends, so the whole structure is cylindrical. For the planar slab, we saw this is like a slab, right? So it extends infinitely in one direction, the Y direction, and then there is a slab in the X direction, and then it extends into the Z direction. So you could have in general any waveguide like this, right? And some again like refractive index structuring. So this supports some modes which are traveling, right? So this mode in general, I can write something like, so I take the electric field is a function of position, right? So the time dependence again, let's consider monochromatic wave at some particular frequency, right? So this for a mode like this, I can write like a transverse mode profile, right? And then traveling with the propagation constant z, right? So for the slab waveguide, this was just a function of x because the structure was invariant in y. But for any 2D structuring, like for in an optical fiber or something, this will be of course a function of both x and y. So this could be, for example, for a fiber, we will take this in the cylindrical coordinates, right? So we will write it like that. It doesn't matter. Right, so this is the mode profile, and this is the propagation constant. So these two properties are basically what uniquely define a mode, right? So each mode has a different mode profile and a different propagation constant. So as we saw for the slab waveguide, and true for any general waveguide, is that we have only a discrete set of modes, right, given by some index, then we could do 0, 1, 2, 3, right, and each of them have a specific value of this theta, right. So if I look at the spectrum of beta, in the continuous range of values that it can have, only specific values correspond to modes, right. So for example, this will be like, for example, if I take TE modes, then this is beta for the actually it will be the other way around. The highest will be like right. So we have discrete values which correspond to modes. Similarly for TM, we'll have some values like this, right? And all the values in between sort of don't correspond to modes, right? So in the spectrum of beta, the continuous values that beta can take, right? So let's I mean, you can even start from 0 and then like, so you'll get k0 n2 somewhere and then k0 n1 somewhere, and all the modes lie between k0 n2 and k0 n1, right? So all the rest of the region, so apart from these discrete values, this shaded region basically doesn't correspond to any guided mode, right? So they correspond to what are known as radiation modes. I mean, they're not modes as such because they're not guided, right? So if I launch, for example, if by some technique I'm able to launch a wave here with some particular value of beta in between, that will just leak out. Okay, right? So it will radiate away. It won't be guided, which means like the mode profile won't remain constant and the power remain constant as the mode is guided. The mode will just eventually leak away, so or radiated away. That's why it's called radiation modes. Okay? So they're not modes as such, but they're sometimes referred to as radiation modes. Okay. So most of the space of beta is basically just radiation modes. Only these some discrete values correspond to the guided modes. So these guided modes satisfy some properties, right? So for example, the guided modes are orthogonal to each other. Right. So what do we mean by that? So let's take the field profile for a mode I. Right. So I is some integer. And if I cross it with another mode j, right? Again, so j is another integer. And so now, for example, if I compute the pointing vector in the z direction, but take the electric field from one mode and the magnetic field from another mode. Okay? And then integrate over cross-sectional area. So this gives me power. Right? So I will only get a finite value or non-zero value when I is equal to j. Okay, so if I is equal to j, which means I'm taking one particular mode, index I, and then calculating the pointing vector, then I'll get some power. But if I take different modes, then I'll actually get 0. Right? So this is a Kronecker delta function. So it's 0 if I is not equal to j, and 1 if I is equal to j. Okay, and if you normalize the modes, something like this, right? So the ith mode, so I have some field amplitude here, and then some field profile. Right. So for example, for the slab modes, these were like cosine kappa x or sine kappa x in the core, and then exponential functions in the cladding. Radiation modes. Yeah, I mean, they exist, right? But the point is that if you like in the waveguide, eventually only guided modes will exist, right? So again, you're right. So depending on the input profile that I launch, again we take this overlap integral, right? And some of the power in the input field profile that I launch could be corresponding to radiation modes. Okay, so that power will get lost, and only the overlap with the guided modes will get guided. So But eventually, like if you after you look at some length of propagation and then see what is being what is guided within the waveguide, then only the guided modes will survive. And if I carefully engineer my input launch condition, then I can ensure that basically most of my power or is excited in the guided modes that I want.
Excuse me, sir.
Yeah.
Sir, we had seen that for betas lying in between K0 N2 and K0 N1, we get guided modes. So, what a figure you had drawn there, interval between like in between beta TE1 and beta TE2, you are calling them as radiation modes.
Yes. Right. So
But they are
because sorry.
but they are falling in the interval of the guided modes.
Yes. Yeah. So of course, so beta less than K0 N2 is obvious, right? So that they will obviously go into the cladding and radiate and then propagate in the cladding. But even for values which are not corresponding to the mode index, right? So these values are sort of, what to say, physically difficult to excite within the guide, right? So these values of beta are actually, because they don't propagate within the waveguide, right? But so there are various ways of coupling into a waveguide from free space, right? And so basically how you tune or how you decide the coupling conditions, like for example, like you could use a lens and then focus the light, or there are like these prism coupling techniques, right? So you have a prism on top of a waveguide and the light comes at an angle, right? So for example, what angle do you decide the light coming into the prism, right? So basically you try to do some wave vector matching so that the free space wave vector component, so you're coming with some, so let's say you have some prism like this, you're coming with light like that, right? And so when it gets reflected from the prism here, there is some evanescent wave here which gets coupled into the guide, right? And now which mode it will launch will be decided by what is known as sort of phase matching, right? So if this is some free space wave vector K0 and this angle is theta, then K0 cosine theta is sort of the angle or sort of component along the propagation direction in the guide, right? So if I choose theta such that K0 cosine theta is matched with some particular beta here, right? Then that mode will be guided efficiently, right? But now if I change theta so that K0 cosine theta corresponds to some value here in between, then it won't excite a guided mode, right? So the evanescent wave which gets coupled here will eventually just leak out, right? So if I want to efficiently couple from my free space into the guided mode here, I have to choose this angle very carefully such that K0 cosine theta corresponds to beta for the guided mode, right? If it's not, if the angle is different, then it will lie somewhere here, and then whatever power is coupled into the waveguide will just radiate away. Is that clear?
Yes, sort of clear.
Right, so it's something like, okay, what if I launch a profile, something like this, but where the beta does not correspond to one of these solutions, right? So at the input of the waveguide here, at least mathematically, I could start with some profile like this, right, with a beta not equal to this, and see how that mode evolves, right? So you see that if this beta is not equal to one of these values and somewhere in between, then basically the field profile doesn't remain constant like this. I mean, eventually it just leaks out, right? The solution doesn't remain constant like this if the beta value is not, right? Again, when you plug this into the wave equation, then you'll see that basically as it's propagating in Z, the amplitude will just keep going down, and So the wave will exponentially decay in Z because it's radiating away. Okay. Mode like this, so some amplitude times some mode profile function, right? So again, as we discussed, this is sine, cosine, or exponential in the cladding, right? For different waveguides, this will be some different functions which correspond to the solution of the wave equation in that structure, right? So basically, it's convenient to normalize the mode like this, such that the integral of this mode profile function is 1. Or the mod square, right? So then
Screen is black again.
yeah. So it's convenient to normalize the modes like this, such that like the integral of the mode profile is 1. So that, for example, if you calculate the power or something, it just depends on mod E naught square. Right? So in this case, you can normalize the mode like this. Then for any I or J mode, sorry, is there a question? Right, so if I take the mode profiles for two different modes which are normalized like this, then I can write the normalization condition like that. Right, and you can easily check this for the planar slab waveguide you take. Right, so it's very easy to check. For example, for if you take I and J as one is symmetric and anti-symmetric, then immediately you get 0 because one is even, one is odd, right? If you take the same mode, of course, then you get some finite value, right? But you can also check for two different symmetric modes, right? So the values of so if you take cosine kappa 1x, cosine kappa 2x, the kappa 1 and kappa 2 values will be such that this integral is 0. Okay, so I guess we are out of time. So this directly comes, this orthogonality condition is directly coming just from the wave equation. Okay. So maybe next class we'll see how this comes about directly from the wave equation. Okay. So this is something similar also, for example, in quantum mechanics. Right, you solve the Schrodinger equation for a potential, and then the eigenfunctions you get are usually orthogonal. Right. So it's the same thing here, and it's the same thing because the equation that we have is basically the same as, it has the same form as the Schrodinger equation. Right? So whenever you have a differential equation of that form that we have for the wave equation, right? So you have a double derivative d by dx square, or d square by dx square, right? And then some constant which or some function of x, right, which defines your potential, and then you look for the eigenvalue, which in this case is basically beta, right? So the solutions, the eigenvalues are beta. So when you have this second order differential equation of this form, then the solutions have to satisfy this orthogonality condition. So next class we'll see how that comes about and discuss some further properties of the modes, and then we'll move on to a graded index waveguide. So here so far we've discussed a step index, right, with constant index in the core and cladding. So we'll discuss how to solve for the mode in, let's say, if you have a graded index slab, right? And then look at specifically some solutions which you can, some profiles where you can solve exactly, like for example the square law profile. In that case, you can exactly solve the wave equation and get modes like we did for the step.